theoretical example. Suppose U1, U2, U3 up to UR, W1, W2 up to WS is linearly independent subset of a vector space V. Okay. Show that LUI intersection LWJ is equal to 0 element, where what is LUI? This is L. Okay. L. Sorry. This is L. So where LUI is a space generated by U1, U2, UR. Similarly, LWJ. What is LWJ? It is a space generated by W1, W2 up to WJ. We have to show that their intersection is 0 element. It is obvious that this 0 element belongs to their intersection. But is their intersection belongs to 0 or not? That is a subset. 0 itself is a subset of their intersection. But is their intersection is a subset of the 0 element? That's the point. So we have to prove that. Okay, let me take one element V from this intersection. LUI intersection LUWJ. So I have taken one element from their intersection. Then this V belongs to, because it is intersection, it is belonging to LUI, and V is also belonging to LWJ. And because it is the space generated by the vectors U1, U2, U up to UR, which means every element of this space is a linear combinations of their generators, right? So let's take scalars. So there exist scalars. Let me take them as alpha 1, alpha 2, alpha 3 up to alpha R for use, and beta 1, beta 2, beta 3 up to beta S for these WJs, right? So V is equal to, so every element of the space is linear combinations of their generators. So alpha 1 U1, alpha 2 U2, alpha 3 U3 up to so on alpha R U R, because it is R in number, and every element of this space is a linear combinations of their generators. So it is V is also equal to beta 1 W1, beta 2 W2 plus beta 3 W3, so on beta S WS at it as it is, S in number. Now V is equal to this linear combination. V is also equal to this linear combinations. Can I write these two equal? So alpha 1 U1 plus alpha 2 U2, so on alpha R U R is equal to beta 1 W1, beta 2 W2, so on beta S WS. Let me take this summation of betas to the other side. So alpha 1 U1, alpha 2 U2, alpha R U R plus negative of beta 1 W1 plus negative of beta 2 W2, so on negative of beta S WS is equal to 0. Now since we know that it is given to us that U1, U2 up to UR and W1, W2 up to WS, these are all linearly independent. This is already given to us. These are all linearly independent, right? Now because these are linearly independent, which means all these alpha 1, alpha 2, alpha R, beta 1, beta 2, beta S, all these scalars are equal to 0? Yes. So which means all these alphas and betas is equal to 0. Okay. So therefore, but these V is equal to the linear combinations. Now as alpha 1, alpha 2, all these alphas are 0. And V is equal to all these betas are 0. Which means V is equal to 0. So V is equal to 0. This implies V belongs to this. Okay, from where we have taken V? We have taken V to be the element of this intersection, which means if V is belonging to that 0 element, so and V is belonging to this, so this whole intersection is subset of this 0. This is how we write. So one is their intersection is subset of 0, and second, but we know that 0 itself is a subset of this. So therefore, from this 1 and 2, we can say that their intersection is equal to the 0 element. Okay, fine. All right. Have a nice day.